Hi, everybody, and welcome to week 2 of Astronomy 120. We're going to continue the discussion. Basically, week 2 is posted on Canvas. I'm hoping that you guys have had already a chance to go through it. There are assignments in this week also. Don't forget that for the most part, as a guideline for every week, you have the objectives component, which is should be on the top of the module. So look at that, go by it. There are assignments from previous week, and there are assignments also for this week. So I'm hoping that you guys basically get into that habit of at least to have a sense of how the workflow for this class is going. Also, you notice that at the bottom of each module, there is the recording for this class. I know you guys are here live, so probably you're not going to be paying too much attention to that, but I'm hoping at least for those who are watching this recorded, at least they know where to go to find the proper resources. So this is basically in terms of the workflow. I will follow up with this basically a class with a message mainly toward the people who are not attending live, because there are quite few of them, to make sure that they're aware of at least these two things: objectives on the top and this week's live recordings at the bottom. In between, there is all kinds of things. There's content, there's assignments, there's discussions, there are stuff that is needed for this week or for that particular week in general. Okay, so this is in terms of the workflow. I still at this point see that a lot of people are not on the online textbook resource, which I assume that you guys then have access to the book somehow, either in a printed form or at least the resource that I have available for you guys on the publisher's website. So this is in a nutshell of how things are organized. In terms of this week, we have 3 units that we need to go through. Unit 7, Unit 9, and then we're going to defer Unit 8 to Thursday. It's a big Unit 8. It deals with the moon, basically phases. It deals with the moon motion and how it's related to Earth and everything. It played actually a major role in terms of determining the overall theory that we use for understanding the solar system, and also for exo solar systems, if you want to call them that way, or extra stellar systems. As a matter of fact, it can also be used for the stars. What I'm referring to in here is that the theory of Mr. Newton was based on his observation of the moon and how it moves around the Earth. So it's a critical piece that we have to understand. In addition, why Unit 8 need to be deferred and has its own lengthy discussion is because of something that we will have down the road. We will have a project down the road, and that project will rely heavily on our understanding of the moon phases. The project basically will consist of you guys going outside for 4 nights, not consecutive nights, 4 consecutive weeks, a night of each week, and monitoring the moon and documenting its phases. So we really have to have Unit 8 basically done. In addition to the fact that we will have at least one problem that I'm thinking that we have to go thoroughly through. I have the book in here, I'm trying to find the page. From Unit 8, that is. It's on page 68, and it's problem 16, okay, from page 68, because you're going to make a prediction based on what we know today. When is the next lunar eclipse or solar eclipse is going to happen? And you're going to do something that is a little bit fancy in there. So we're going to have that problem thoroughly discussed when we meet next time on Thursday. So that's basically the idea of the plan. So we're going to do 7 and 9 now, and then we're going to do 8 later. Okay, so that's the plan. Sounds good? Okay, very good.
Yeah.
Thank you, Alex. Okay, very good. So here is Unit 7. Again, you have the PowerPoints. They serve just as a guide. Also, the discussion that we have in here serves also as an additional resource. It's still, the book is really actually a great reference for you guys to go through it. So if you have any questions about that, if you think that there are things that needs to be further explaining or demonstration or something, I'd be more than happy to discuss that. Okay. Brittany, did you get the answer or not yet? Page 68. Yeah, page 68, problem 16. Got it? Okay, it doesn't matter. I'm going to probably post it on Canvas anyway, so that you guys have that. Not only that problem, but there's probably at least one more. Okay. So anyway, so as I was saying, I'm hoping and I'm counting actually on you guys doing the actual reading, because you're going to be tested on that. So you really have to make sure that you do that. Okay. So that's the whole plan. Again, Unit 7 deals with the day and how the day is defined. You see from this units already, from what we covered so far, astronomy plays a major role in everyday life in general, not just in science, which is true. Astronomy was at the forefront of the scientific method and how it was developed, whether in physics, whether in biology, whether in chemistry, or whether even modern other fields that are basically trying to incorporate the scientific method in their approach, like psychiatry or psychology and all of the other fields. So the point being in here is it plays a role in our everyday life. Like, for example, time. This is something we take for granted. If you ask somebody what time it is, they will look at the watch and they tell you right now it's 2:18. Okay, so that is something we do on a daily basis. But that is rooted in something that we have to define. Namely, what do we mean basically by day, and how the day was divided into at least chunks, some units, turned out to be 24. And then, and that there is a problem right there and there, okay? There is a problem right there and there. What do we mean by day? Is the day starting from sunset to sunset? Or is it from sunrise to sunrise? Or is it from noon to noon, and so on and so forth, okay? So this is something that we're going to go through. We're going to try to understand also daylight hours and how they change from latitude to latitude. Turns out if you are on the equator, your daylight and daytime and nighttime, they're the same. They should be about 12 hours, okay? But if you are in the northern hemisphere, depending on the season, there will be more daytime in the summer and more nighttime in the winter. If you are in the southern hemisphere, it's the other way around, okay? It has to do with the tilt of the Earth and because of the sun basically changing locations. And we discussed that in previous units, okay? So this is something that is, and then we're going to also talk about the time zones, and the time zones solve a major problem. Without them, we will not be able to basically tell what time it is and things like that. They're actually necessary, okay? You take a big chunk of a region on the planet and you give it one time, okay? It's a 15 degrees one way or the other. Within those 15 degrees, you have a specific unit of time, and that is 20 for the entire planet, and then we have no problem. Otherwise, I mean, right now, my noon here in Loma Linda is most likely different than the noon just in here, Palm Springs, or the noon in Los Angeles, because the sun is moving and the Earth is actually spinning. As it spins, the apparent path of the sun changes. So if I'm looking at the sun above my head as being noon, the zenith, then it still needs to make up that difference to move toward LA, or it already did it in Palm Springs. So I really have to be careful in here, even on this small distances. But it turns out all of this region, whether you're in Palm Springs or further east, or you're in Los Angeles or further west, it's still the same time zone. So we're looking at the same time, 221. That is actually solves the major problems I was saying in terms of communications. Okay. Then we're going to talk about something which is very important, and that is because the Earth actually, when you measure how many seconds in a day, it turns out that there is an extra fraction of a second. So if you're careful enough, you have to really be able, you should adjust for that. Okay, that is what we call the leap seconds. Okay, so it's not exactly 86,400 seconds per day. There is an actually fraction of a second left, and that is going to accumulate over time to become minutes and probably or at least seconds over a century and so on and so forth. And that's going to present a major problem. So you need to adjust for that. So that's basically the whole point of this. Okay. So again, the definition of a day needs to be refined further. Is it from sunset to sunset? Or is it from sunrise to sunrise? Or is it from somewhere to somewhere? The reason why it's really not good to do the sunset or either to the sunrise is because it changes depending on the season. Okay. In the winter, in the northern hemisphere, the sun is closer to the horizon, so it rises from specific points above the horizon. Whereas in the summer, it rises further away. So defining it, you will have shorter days basically in the winter, whereas shorter daytime in the winter, whereas longer on the other side. So it's going to be a problem. So it's really not a good idea to use that. So the convention is the following: you go wherever you are. It doesn't matter where you are on the Earth. You look due north. I'm looking at due north right now, and then whatever behind me is due south. Okay. Then I draw an imaginary line in the sky, and when the sun passes through that line above my zenith, so above the point immediately above my head, because if you are on a circle, you could actually draw that line whichever way you want to. Okay. Yes, you have two lines, but you can go like this if I want to go from here to here on a sphere. So I'm trying to go from here to here, or I can go from here to here, or I can go from here to here. So there is an infinite way of doing this. But if you restrict it just on your zenith, then you have only one point that you're going to go through, and that is called the local meridian. So this is your local meridian. Everywhere you are on Earth, you have your own. Okay. And that is fixed. When the sun passes through that line, when the sun is exactly on that line, it doesn't have to be immediately above your head. It doesn't have to be on your zenith, but as long as it crosses that line, that is actually noon by definition. Okay. Anti-noon, when it's in the morning, anti-meridian, AM basically, when it's before noon, so that is called the AM. Post-meridian, or PM, is when it crosses to the other side. So that's where the AM and PM are coming from. Make sense? Sounds good? Very good. Thank you, Alex. So the point being in here, there is actually a problem. Let me explain what the problem is. The Earth is moving around the sun. It takes a year to go once around the sun, but it's also spinning around its own axis. So as it spins, it makes a full cycle, it makes a full rotation. Let's say, for example, this is the position of the sun from this picture. So I'm standing in here looking at the sun. It's on my local meridian. It's noon, basically. If it spins a full cycle, it has moved. It moves. It's not sitting still. It moves to go to complete its 1 year. So as it moves, my noon is not really noon now if the Earth just rotates one full cycle, one full circle. I have to wait an extra almost 4 minutes for it to catch up so that the sun again crosses the meridian. Okay, so that is an additional time. For me, the way I define the day is from noon to noon is 24 hours. So this must be less than 24 hours. I need you to remember this because down the road, we're going to do a problem with Venus. And it's very critical to understand the day on Venus and the year on Venus so that we have that understanding too, because Venus spins extremely slow around its own axis and moves faster actually around the sun. So this problem is exaggerated a lot for Venus. For us, the Earth is just spinning fast enough so that the difference is only about 4 minutes. But it's actually several months, if you want to, on Venus. So the problem is really a lot worse actually for other planets that spin extremely slow around their axis, whereas they move fast enough around the sun, okay? Or vice versa, okay? So the point being in here is that you need to wait for those extra 4 minutes. Actually, the day is 23 hours, 56 minutes and change, and 4 seconds and some change. So it's actually not exactly 4 minutes difference, but it's 3 minutes and 55 seconds and some change. So it's 3 minutes and 55 seconds. Okay, so that's basically the difference between the solar day, as we define it from meridian to meridian, and this day, which is really actually in reference to whatever any background object in the sky. Okay. Yes, Alex.
How does daylight savings change contribute to this?
Okay, the daylight savings, we're going to talk about that one later on. It's because basically the sun in the summer, or at least at the solstice exactly, or around the solstice, rises actually earlier and sets later. So what you do in this case, you adjust the clock so that to save, if you wish, energy when it comes to later on, so that the lights do not turn on early enough, at least when it's lit already. So that's the idea behind it. That's the whole purpose of it. Okay, but at least the sidereal day, which is what we're talking about, sidereal day, which we're actually referring to in this case, refers to the actual motion of the Earth around its own axis with respect to far away reference points like the stars. Take any star, okay, and see it now on your meridian when it crosses your meridian, and wait for it when it crosses your meridian the next time around. It turns out, because we already defined the hour as being a day is 24 hours, that time has to be less, because the Earth is moving actually. So in order for the noon to happen, in order for the 24 hours to happen, the Earth has to actually make an extra, if you wish, spin on its own axis to make up for that difference. I hope you guys see the difference between the sidereal day and the solar day. The solar day is by definition from noon to noon, and noon is when the sun crosses my local meridian, wherever I am at, okay? That is 24 hours. So that is fixed, okay? However, this is related to a real motion of the Earth around the sun, and it's around its own axis. Because of that, the Earth has to make up for that difference to make the 24 hours. So it's spinning a little less to make up for that difference. Make sense? Okay, very good. Thank you, Alex. Okay. So again, the daylight, I mentioned that in the intro, basically the daylight changes, depends on the season, okay? Because of the tilt of the axis of the Earth, the sun rises early and sets later because there is more time of exposure to the sunlight, okay? In the summer, in the northern hemisphere. And it's the opposite is true in the southern hemisphere. That happens because of the tilt of the Earth. In the winter, for us, basically, in that winter time, they have more exposure to time. Our nighttime then is less in the summer and more in the winter, and it's the opposite in the southern hemisphere. Okay, so the time can be drastic. For example, in North America, for the most part, the summer can be about 15 hours. Okay, and the summer, the daytime can be about 15 hours. Okay, whereas the nighttime can be the difference, which is about 9 hours. And the other way around is true for the winter. Now, above a certain level, above a certain point in latitude, as a matter of fact, is 66.5. Where did we get 66.5? Remember, you have 90 degrees going from zero, from the equator all the way to the North Pole, which is 90 degrees. Okay, the Earth is tilted by 23.5 degrees. So any location that is 23.5 degrees from 90 degrees, 90 minus 23.5 is exactly 66.5 degrees. So if you happen to be at 66.5 degrees, there are times, especially during the summer solstice, where the sun never sets, rises and stays above the horizon. Rises, goes peak, and then come back and stays above the horizon. In other words, it's all day. And the opposite is true in the winter. The sun never rises above those 66.5 degrees of latitude. Okay, and we're talking Alaska or very far north in Canada or Iceland and places like that. So that's basically what we're talking about. Whereas in our location, remember, we are at 34 degrees in latitude. 34 degrees, we will never see this phenomenon. Okay, we are well less than 66.5 degrees. So we should not have that problem. And it's true also for the southern hemisphere. Southern hemisphere, except that the picture is reversed. Again, when it's all day in the northern hemisphere, above 66.5 degrees, it's all night below 66.5 degrees in the southern hemisphere. So the picture reverses. Okay. So again, this is how much exposure. This is actually the reason why we have the daylight savings, at least in some countries that adopted that approach. So it depends on the politics sometimes and whether or not you want to go with it or not. Okay, because street lights, especially, and basically a lot of things, they go on automatically. For example, at 6 p.m. You know, in the summer, 6 p.m. is very light, very much light. Okay, so you'd want them to be. You would want 6 p.m. to happen later, very close from sunset. Okay, so that's why you would want to have this thing in here. And it's apparently a lot of logistics involved in setting up the time or changing it. So much setting up the timer on those things. So it's much easier to change the clocks. Okay, that's apparently what they're doing. Anyway, we come to the time zones, and I mentioned before that the entire Earth is divided into 24 zones. Okay, remember it's 360 degrees, full circle. But it's also 24 hours. So if I want to find how many degrees correspond to an hour, all I have to do is divide 360 by 24. And if you have a calculator handy next to you right now, you take 360, you divide it by 24, you will find that it's 15 degrees for every hour. So as long as you are 15 degrees within an hour, that is basically how much you are. Let me share with you the calculation, because it's very critical in here to do it right, because I think last time I messed up with it, at least when I was teaching this class. And you might find my old recordings and you might see the error in there. So I want to catch up that one in here. So let me stop sharing. Oh, let me launch first of all the app that I need, which is usually OneNote, because that helps me. Oh, my keyboard is here, sorry. Okay. And page, okay, and let me share with you, stop sharing. Let me share with you the calculator or the OneNote share. Okay, so again, okay, I didn't think Am I sharing this? No, I'm not. Where is the share? Okay, very good. I'm sharing now. Beautiful. You guys see the OneNote? Okay, very good. Thank you, Alex. So anyway, so what we have in here is, oh man, I don't want this pen. I want a different pen. Okay. My keyboard is out of the way there. So we have 360 degrees divided by 24 hours. That should be 15 degrees per hour. Okay, plus 15 times 24 is 360. Or is it? Just make sure. I don't want to. Okay, 15. You guys need to do stuff with me in here. I should not be, because I make a lot of mistakes. So I really want you guys to. Okay, that's correct. Okay, so that's the for each zone, it's 15 degrees. What I want to do next is, we know the Earth radius is about 6,500 kilometers. This is the radius of the Earth. Okay, in other words, the Earth is a sphere. And this is what I talk about the radius. If this is the center of the Earth, this is how far it is. So this is the radius of the Earth. Okay, there is a formula we will need for the circumference. The circumference is equal to 2 pi times the radius. 2 pi is just a number, okay? Pi is 3.14, and 2 pi is 6.28, okay? So far, so good. So what I want to do is, if I go around the Earth, starting from this point, and never turn around, stay on my latitude of 34 degrees, of course, provided I can walk on the water or something like that, I may have developed some sort of a other skills. Anyway, so go around the Earth and come back to the same point. That is what we mean by the circumference. So the circumference then in this case, which is C, the symbol for it, is 6.28 times 6,400 kilometers. I want you to remember the answer of this multiplication because it's going to come in handy later on, okay? So we have 6,400 times 6.28. Obviously, I'm hoping that you guys have a calculator and you're doing this one. You're going to find 40,100 and some change. I'm going to make it approximately 40,000, okay? The reason why I'm saying that this is not exactly 6,400, this is about 6,380. So I rounded up this one in here. So I'm just taking an approximate value. So it's not exact, okay? I'm just trying to find a rough number. Okay. This is the circumference of the Earth. What I want to find is how far do I need to go to change time zones? That's the question. In other words, I will change the clock as I go around the Earth a distance of 40,000 kilometers. I will change the clock from whatever clock is to another time zone, to another time zone, to another time zone. I know I have exactly 24 time zones, okay? My question is, what is the distance between each time zone and the next time zone? That's really the question I need to answer, okay? So what I need to do is take 40,000 kilometers and divide it by 24. That should give me the distance between two time zones, okay? So that is really the question that I have in here. So what I need to do, again, take the number that I came up with, which is about 40,000, 4000, and divide that by 24, okay? And that is the answer that I was hoping for. It's about 1,600 or 1,700 kilometers. Or roughly about 1,000 miles. That is the question. So it's either you answer it 15 degrees per hour. That's good enough. Or 1,000 miles per hour. Okay. So the question for you guys now is, what is the difference in terms of time zone between the Eastern time zone, which is, let's say, New York or Washington, doesn't matter, and Los Angeles? Do you guys know the difference between these two time zones? Just interject. Right now it's 2:41 in our case. Do you know what the time is right now in New York, for example?
It's like it's 3 hours ahead, so 5:40.
3 hours, very good. That's really the it's about 3 hours. Makes sense to you guys? So my question then is, how far is the distance between Los Angeles and New York, roughly? I don't need exact number. Remember, every hour is about 1,000 miles. And Vanessa said that we have about 3 hours. Yes, that's correct. Okay. Yeah, that should be about that number. It's slightly less. Actually, I drove once from here all the way to Virginia Beach in Virginia, and it's about 2,700 miles. Okay. So it's close enough. So that's 3 different zones, okay, that you're going to account for. You guys see the connection between the geography and the math that I was developing earlier in here? You take 360 degrees and you say it's 24 hours. So that means each hour must be 15 degrees. That's one way. The other thing, and I went through a long way to find the fact that there is a 40,000 kilometers if I walk from here and come back to here, not leaving my latitude, not going north or south. Although if I do that, there will be very little difference because the Earth is very close from circular. I mean, it's not going to make much difference. So if it's 40,000 on one side, it's slightly less on the other side. But the point being in here is you go around the Earth in one shot. Don't wander around though. Don't go up and north because then you're going to travel more distance. Okay. So if you do that, you're saying, okay, 40,000 kilometers is about 24 hours. It turns out that that number, when converted to miles, is about 1,000 miles. Then I asked, what's the time difference between the Pacific Standard Time where we are and the Eastern Standard Time where New York is? And you said that it's about it's 3 hours. So that put us about 3,000 miles. The other question is, what is the difference between us, for example, and Greenwich? We are at a -8. So that means that our time zone is -8. That means that we have about 8,000 miles different from here to France, for example, or Africa, for example, at least that part of Africa where the Greenwich passes through, or England or London or something like that. So that is how you have at least a visual of things. Make sense, all of this? Things? Okay, very good. If it is hard for you guys, please let me know too, because this is the type of math we will be doing in this class, okay? As I said in the intro last week, is we will be dividing a number by a number and seeing what it means, or multiplying a number by a number, and this is what it means. And this is real daily life experience things that we deal with. This is something that we deal with. In other words, do I need to do an oil change before going to driving across country? I have 3,000 miles, depending on the make and the model of the car, you may need to. So that's a practical issue that you need to think about, okay? So that's basically how you divide things, how you do things. So 15 degrees is about 1,000 miles, or about 1,700 miles, kilometers, I should say. Okay, so let me continue with the PowerPoints. So again, the time zones were divided. We call the line that passes through Greenwich in London, as you can see from here, that is the 0 degree, that is called the prime meridian. So that is actually a selected meridian. Remember, you have your own local meridian. Everybody does, okay? And you could be sitting next to one another on the same table, but you have your own and the other person has his or her own, okay? So you could be different completely. So local meridian, well, not completely, I mean, they're very close from one another, but you could be different, okay? Theoretically, they are different, okay? But the prime meridian is only one. That's by convention. They agreed on, that's where the 0 is. So if you look all the way to the Pacific, you will see we are at -8. So the distance between the Pacific all the way to anywhere on this line is about 8,000 miles. Okay, so that's basically how you can do the math, because one hour is about 1,000 miles. So that's basically how you can do the math. Between us, for example, and Hawaii is about 2,000 miles. Now here is where it becomes a little bit of an issue. Because of the politics, some islands, for example, here, they would want to be on the same time. So they move the timeline across to accommodate for that. The same thing in here, for example, the plus or -12. This is called actually the international dateline. The international dateline is the opposite to the prime meridian, and it's critical because that's what defines the next day. In other words, you could be sitting on one side in here of this line, and your friend sitting on the other side of the table, on the other side of the line, and he or she is in yesterday, and you are in tomorrow. That's what the daylight, the daytime changes. So if you watch, for example, the New Year's Eve, it starts from this line and continues all the way until basically passes through. So London, for example, Australia, first of all, will have its New Year's Eve, and it continues all the way until it reaches us in here in the Pacific time zone. So that's how the times are defined. Again, sometimes the lines are not exactly lines in here. For example, -3 and Iceland is not the same everywhere. So that's basically because of the politics that is involved, and the geography also plays a role. You would want to divide it, for example, based on some main features of the Earth, like, for example, mountains or whatever you have. So this is basically how the time zones are defined. Okay. Again, anything on this side is a positive, so it's ahead of the prime meridian. Anything on this side is negative, or it's behind the prime meridian. In other words, noon will happen in here, and later on it's going to start happening in the rest of this side of the planet. Noon has already happened in here before the prime meridian by this amount, okay? And for some reason, most of Europe is actually ahead. Even Spain is ahead of, as you can clearly see, it should be on the west, should be actually behind, or at least on the same time zone as Greenwich, but it's not. So most of Europe, and actually a great part of Africa, where this prime meridian passes through, they're actually ahead, and so on and so forth. And some countries, for example, they don't have a prime meridian at all in that. Case in point, Morocco and here in Portugal, and they go by it. So that's basically how this thing is done. Make sense? Good. If it's not clear, please let me know, okay? Or you can go through. Very good. Thank you, Vanessa. Go through this and then try to have it clear, then let me know, okay? Again, already Alex, I think, is the one who asked about the daylight saving time, and I already tried to answer it. Not everywhere, for example, if you look at the United States, Arizona in here does not observe the daylight saving time. Sometimes they have the same time as we are, sometimes they're ahead of us. So that's some of the places that don't observe it. And the purpose of it is actually to save energy. That's why it's called daylight savings, okay? And that is to allow to take advantage, if you wish, of the extended daylight in the summer, to take advantage of it and basically accommodate for the saving energy, especially when it comes to lights and so on and so forth. A lot of countries Europe, basically North America, has adopted that for the most part. Not everybody did. And actually, the Southern Hemisphere, they have a different approach to this one, and that is the summer. They have a southern summer daylight saving, so the picture is reversed in here. And not everybody actually has it. I think Angola, and parts of Brazil, and parts of Australia, and so on and so forth. Okay, because they are too far south. Okay, for some reason, South Africa does not have it. Anyway, the point being in here, this has to do with time, especially when it comes to day. And still have plenty of time to go through the next unit, unless you guys have any questions. So let me stop sharing. Share with you in mine. Share. Mine. Okay, as I said before in the intro, we're going to leave Unit 8 to separate basically discussion for reasons that I'm hoping will become clear. As I was saying, it's very important to have that discussion separate because we're going to go through some examples and how to do calculations and things like that. Okay, so the word month is coming from moon. That's no secret. Okay, how many weeks in a month? That is actually the number 7 was adopted for probably related to the moon. And this is actually from Unit 8, the discussion on the moon, because the moon turned out to be also have a sidereal cycle and also a lunar cycle. Okay, if we look at full moon to full moon, for example, or new moon to new moon, it's 29 point something days. Okay, if we look at the moon as it spins on its own axis, it's less. It's about 27 something days. In either case, if you take that cycle and you divide it by 4, you'll find 7, because 28 divided by 4 is about 7. So that is probably some of the ideas, but the most probably reasonable assumption here has to do with the at some point, at least in the French Revolution, during the French Revolution, they adopted a different period for the week. Okay, they decided that the week is about 10 days, but that did not work out well. Imagine if it's really 10 days a week, then you guys will be lucky because you will be working extra 7 days. I mean, you will be working 7 days, or at least, no, I'm sorry, 8 days and 2 days off. That's too much, isn't it? Anyway, so let's go through the reasoning probably why that is. It has to do probably most likely with the object that we can see in the sky. So let me stop sharing and let me share with you my OneNotes again to explain the relationship. Okay. I know some of you in here, they speak Spanish fluently, and you probably can help me out in here because I don't, I'm sorry, I wish I could. Okay, so first of all, moon. That's a big object that we see on a day every night in our sky. Okay, the other object that I'm going to talk about is Mars. That object also is something that rotates on the Earth around on a regular basis, at least from our vantage point. I know it doesn't rotate all around the Earth; it goes around the sun too. But for me, going outside, night in, night out, I can see that object moving locations with respect to my reference points. Okay, so that's another object. The third object that we're going to talk about is Mercury. There is a reason why I'm putting them in this order, okay, and you will see it clearly. Okay. Then after that, Jupiter. And after that, Venus, Saturn, and finally the sun too. Don't forget that the sun also, from my vantage point, it goes around the Earth. As I was saying in the beginning, from Unit 7, the day is defined, the sun moving from noon to noon with respect to my reference point. Granted, and I know you know that, and I know that the Earth actually is the one that is going around the sun, not the sun going around the Earth. Okay, but that defines the year actually, not the day. The point being in here, the sun also is another object that we can see in here. If I count them in here, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, and this is 7. So most likely that's how the day was divided. Again, you see how much astronomy has influence over our culture. This is something that is inherent from a long, long time, and this is actually from the time of before even the Egyptians. Okay, before so it's an old definition. Okay. Obviously, at least in American in English, the moon is associated with Monday. So you can think of Monday as being the day of the moon. Okay. Mars is Tuesday, and I will explain why that is. At least in French, I know that, and I'm sure also in Spanish too. At least in French and in the Latin languages, at least this is how it's written. Does everybody know how it's in Spanish? Oh, I thought there would be some Spanish speakers in here. Okay, very good. Thank you, Susan. Yeah, so I think I don't want to murder it, okay? So I'm going to write it, okay? Martis, but I'm going to write it correctly, okay? I'm taking your word for it, okay? Anyway, Mercury has to do with Wednesday. Again, if you look at the culture, you will see that these are actually Germanic gods that have associations with the Mars and Mercury, okay? Again, in French, it's actually Mercredi. And again, it's probably true also for Spanish too, because both of them are actually Latin languages. Do you know that, Susan, or anybody else? I was said in. Nobody? Okay, very good. Thank you. I'm not going to try to say it, but I'm going to write it down. Okay. I know it's in French. It's Mercredi. That's very close, probably from the Spanish one, because both of them are Latin languages. Okay. Okay. Again, that has to do with Mercury. Jupiter actually has to do with Thursday. Again, the god Thor or something in the Germanic languages, and it has to do with Jupiter, the king of gods, or in the sky. So again, in French, that's how you do it. It's jeudi, and probably very close. Yeah, okay, very good. It's probably the same thing in Spanish. Okay. And Venus is actually Friday. The day of Venus is Friday. In French, it's vendredi. And probably something similar also in Spanish. Okay, very good. Thank you. Susan, you're a great help in here. Okay, I guess everybody knows what the next one is. Except in French, it's samedi. And I will leave it in here. Okay, very good. Are they different? Gabriel is saying something different than what Susan is saying. Which one is correct? Oh, okay. Thank you. Gabriel is trying to throw me off, okay? Okay. And of course, Sunday is the day of the sun. And for some reason in French, it's completely different. And I don't know what's in Spanish. It's Domingo. They're all different in all three languages. Okay, anyway, had we known, then probably, this is my theory, okay, had we known the other two planets, okay, namely Uranus And Neptune will probably at least will have this many days in the week. Uranus was discovered by Herschel, and when he was looking at it, and then immediately astronomers realized that there was a problem with the path of Uranus, so it has to be disturbed, and they made a prediction that there must be another planet somewhere. Two astronomers, one in England and one in France, and they sent the observation that look for Neptune, for another planet. It must exist in this location, and sure enough, that's how Neptune was. This is a planet that was discovered by calculation. Okay, this one was discovered by Herschel before it. Okay, so the point being in here is that this is how the days are. They came out to be. It has to do with the objects that are the planets, which are the wandering stars, which are star. That's what the planet really means. It's a star that moves around. Okay, versus stars that are fixed in the constellations. If you take any other star, for example, and we mentioned quite a few of them, they don't change their constellations. They stay in their places all the time. Whereas these ones, they move from constellation to constellation to constellation year round. Okay, so they all the time, and they move significantly too. So that's why they were called the wandering stars. And the word planet, really, that's what it stands for. Okay. And of course, add to them the moon and the sun. The sun also changes constellations. We saw that in the signs of the zodiac, how the sun changes from location to location in the year. Okay, so the sun also changes location. Same thing is true also for the moon. So all of these objects, they wander around, except that the sun is associated with the day by itself, nothing else, and all of the other objects are with the nighttime. So that's how the day probably came out to be. Thank you, everybody who helped me with the Spanish words. Okay, and I don't know what lundi in French, or Monday. I didn't say that, and I don't know what that in Spanish is. Okay, we need that too, because we need to complete our dictionary. I need to come back to it some more time in the future. What's Monday in Spanish? Lunas. Okay, that's very close from the moon too. Actually, yeah, same thing with the French too. Okay, the day of the moon. Very good. Oh, somebody knows Italian. Okay, I will save this. Again, look at it. They're very close from the. I don't know if you guys are looking at the chat or not, but you probably need to, because they are very close from the Latin words too, from Spanish and from whatchamacallit, and French. That is very good. Thank you. Oh, man. Is it Chiara, or is it? Am I saying your name correctly? If I messed it up, I'm sorry. Okay. Anyway, let's continue with this unit in here. Share. So that's most likely how we came up with 7 days in the week. Okay. Obviously, we have also the month, which is a big issue. The word month comes from the moon. The moon actually does sometimes 29 days, sometimes 30 days, at least in the lunar calendar. And because the yearly solar, the number of days in the year is actually 365 days, then in that case, there is a discrepancy between, what is it? The number of days and the number of days in the moon, and the number of days for the which is 354 days for the lunar basically cycle. Then there is an 11-day difference. Okay, 11-day difference. And in the old cultures, that's what they were using. They used to use the lunar month as being the month of basically from new moon to new moon, or from full moon to full moon. There are some cultures that keep on still use that. I mean, for the Islamic culture, for example, they use the lunar month until today. Okay, to do all kinds of things for religious purposes and so on and so forth. The Chinese calendar and the Jewish calendar turn out to have a mixture of the two. So what they do in this case is every 3 years, because remember 11 days, 11 days, 11 days, that's 33 days. That's a month basically, okay? They bring up the calendar up to par with the solar calendar. So they are not exactly lunar calendars. They are not exactly solar calendars. They're a mixture or a hybrid, okay? Where they use both of them. They bring up a 13th month every 3 years to make up the difference for the difference, so that they come back basically to the regular cycle, so that the same month happens in the same season all the time. Whereas in the Islamic calendar, for example, this month, for example, would be summer. Wait, 11 years from now, that month is going to be actually in the winter. So the calendar moves around, and that's the problem with the lunar month. It doesn't stick around with the seasons. So, and that is not good. Actually, you want something that is fixed in time, so that, for example, January 1st is known, so that exactly what other dates and dates are exactly known, so that, especially in terms of agriculture, in terms of other things. Otherwise, you'll be moving with it. So again, this depends on the culture, but again, you will see how much astronomy has influence. Because if you are in agriculture, for example, in the old societies, you would want to know when to plant stuff. Is the flood season coming? When to basically plan for migrations, to take all of your herd of animals to another place for grazing and so on and so forth. So you would want to know those times. That's why the calendar is a practical issue that needed to be solved. Okay, so that's why it's important. Again, we have the problem with the current number of days is that the Earth, when it goes around the sun, actually it's not exactly 24 hours times 364. There is a discrepancy, and that discrepancy amounts to about a quarter of a day. So we need to account for that, and that's where the leap year was invented, to accommodate for the fourth day, so that for every 4 years, 1/4 times 4, that is exactly 1 full day to be added. And we chose the month of February to add it in. Okay. I think we introduced and we discussed the entire chapter in the introduction and the objectives. Okay, so again, we mentioned the fact that different cultures have recorded different time, and you have them in here, at least some of the samples. I mentioned reflects the approximate measure of a quarter of a month. So that is probably the reason why we have 7 days. 7 days was actually used by the Babylonians and Sumerians. Okay. And most likely, as I was saying before, it has to do with the sun, the moon, Mercury, Venus, Mars, Jupiter, and Saturn. And think about the other 2 planets, Uranus and Neptune. Had they been discovered, probably the discussion would be why those 2 not included, or you include them, then you will see the number of days has been extended. This is something interesting that I always think about when I come to this point. In other exoplanets, for example, depending on how they evolve, if there is intelligence life in there, how do they solve these issues? How do they arrive to that? I mean, remember, some of the exoplanets that we see, at least according to observations, they spin so fast around their own planets, their own sun, within days, 7 days, 15 days cycle. So that's how much a year is. So those things, and because they're spinning so fast, and we'll learn that down the road about Kepler's laws, they must be very close from their host planet to spin that fast. And because they are so close from their host planet, they will be tidally locked, meaning that there is no day or time on their planet. It's only one thing. If you are living on the other side of the planet, it's all night. If you are on this side of the planet, it's all day. So the concept of day and night, they don't have it. They have either a day, an endless day, so that concept does not even exist for them, or they have an endless night. Or if they live on the border between these 2 zones, the zone that is facing the star and the zone that is away from the star, and they migrate between the shaded area and the non-shaded area. So they have at will when they want to go. They want to go to the sunny area, they go. They want to go to the lit area, they go. So it's not like there is a cycle or anything like that. I mean, granted, even in these situations, probably depending on the planet and how it orbits its own star, and because it's very close, it's probably going to be subject to a lot of tides, basically. Then in this case, probably there is variations around the border where it brings up the lights and dims a little. So it always makes me wonder about those things, how they define their own time, number one. So this is a very good discussion point that probably I'm going to include some other time in here. The other thing also is what happened to them, for example, in terms of their week, for example, okay, if they want to define a lapse of time. Yes, they have the planet going around the star, but do they have other planets in their system? What do they see when they travel to the dark side? Okay, they must see objects, and they start wondering about the other objects also in the sky. Obviously, if they're on the lit side, they don't see anything. They are blinded by their star. So that's the same thing what happened to us during daytime. So these things are interesting. I mean, it makes you wonder what other worlds would look like. Okay, for planets that are far away from their whole star, for them, the star is not probably the source of anything. I mean, take, for example, the moons of Jupiter. The moons of Jupiter, for them, Jupiter is the thing, because they revolve around the Jupiter, and the sun is far away from them. It has less of an effect than what Jupiter does. So all of these things will be scaled differently. I'm sorry, I may sound like I'm going off the topic, but it's an interesting thing to have to do with this thing. Because we're talking about culture in here, and how they define time and how they define length and so on and so forth. And culture is actually defined by this, the environment that you live in. The environment that you live in dictates a lot of these things. Does this stir your interest a little bit? Okay, again, the next item is reasonable periods of time. Again, based on also on some biblical or religious accounts, okay? Because we are, I mean, this is a question from Alex. He says, if you travel in space, is there time? Because we have actually, at least we know now we have technology enough so that we can tell time, okay? We define it now, for example, based on the things that are on this planet. But if you really are traveling in space, there are other things that you can use for time, and we'll come to that. And probably that will answer my question that I raised earlier, namely that there are universal things outside of your own system that you can define. For example, the thing I can think of in here, neutron stars. Neutron stars are beacons in the sky that can be used as to determine basically locations in the at least in the galaxy, and they can be actually used as clocks too. So these are independent of your culture, basically, at least in immediate culture. Okay, these are galaxy-wide events. Okay, but yes, you can. I mean, time is something that is going to be you're going to observe it, unless you're traveling extremely fast. Then you have some other effects that start to take over. Anyway, so. Again, we talked about the lunar month. This is the Islamic calendar from the year 1426. 1426 is about 2008 or 2009. So there is the starting point is different from the Gregorian calendar, and also the months are different. Like I was saying before, the lunar calendar in this case shifts 11 days every year behind the Gregorian calendar, behind the solar calendar, I should say. Okay. Other cultures, like for example the Jewish and the Chinese calendar, it uses a mixture of these two, lunar and solar. Okay, so it's compensates for that every 3 years and brings an additional 13 months to compensate for the difference between the solar and the lunar motions. Okay. As I was saying, the year is not exactly 65 days, but 365 and a quarter. That means if I add 4 of this, it's going to be 4 times 365, but mainly it's going to have 4 times 1/4. So the 4th year, by convention, is a leap year. It's 366 years. Okay. One is a year has to be a leap year. It has to be a leap year if it is a divisible by 4, of course, and it's what is it? It's not an odd number. Okay, So we'll talk about this one because this is immediately related to the problem I was talking about. Problem from units. There is no chapters in this unit 8. Okay, because we need to come back to this problem in here to make prediction in the future. Okay. So modifications of a meeting leap year not divisible by 400. So yes, that's the point. Okay. So if you take a year, for example, 1900, is that divisible by 1400, by 400? The answer is no. In other words, 19 divided by 4 is not exactly multiples, but 2000, yes, 2000 is divisible because you take 20 divided by 4, that's 5. So if there is a remainder, it's not a leap year. If there is no remainder, then it's a leap year. Okay, the year 1600 is a leap year. The year 1600 divided by 400, that's exactly 4. So yes, it is a leap year. The remainder is 0. In other words, if you take your calculator and you divide 1900, for example, divided by 400, you will find that the answer is 4.75. Okay, so it's not exactly 4. There is a remainder. And that remainder makes that this year is not a leap year, okay? In addition to the fact that it also has to be divided by 4, okay? And any number like 1900 is divisible by 4, but that's not the only rule that we have. There is an addition, okay? I want you guys to go through this unit and read it thoroughly, at least to this point in here. Try to understand the leap year and how it works, okay? Again, this is a typical of the Gregorian calendar in here. And these are where the new moons are, just to give you an overlap of the two. Okay, then also we used to do the BC and the, so that's before the modern, so the starting point is an issue also. When did that start? So that's by convention. Now it's the common era. That's the one that we're referring to, instead of the because religion now has tremendous influence over these things. The one that this issues that we're bringing in here into the calendar. So the time, astronomy has an influence over religion and vice versa. So it's rooted there, but now we're trying to be basically a religion. If you wish, putting it aside if we want to, but we cannot really deny the fact that it was there, okay? These are the two units I wanted to cover today, okay? And I'm gonna say this thing about the Italian in here, because I don't know that. Select all. Oh, no. Control C. And I'm going to save it to my desktop. Any questions, guys, you have for me? Okay, very good. Listen, you guys have an assignment. I believe you have a quiz this week in here. Let me make sure I have. Yes, you have a quiz that is due on August 30th. Open the objectives in here. So let me share with you that. Okay, the urgent thing in here is this 2 here. That is very important that we have to finish this 2 this week, okay? The 24th is tomorrow. I know most of you, or at least a lot of you, did this one in here, but if you didn't, this has to be done. And you will hear from me by tomorrow if you did not do this one, at least the 24th. And then you have this 2, which are due this weekend. And September 2nd is where the discussion of this item is. Discussion of week 2 is. So there is an assignment for discussion of week 2. You're supposed to watch a video, read the units, and then come back so this is the assignment in here. Explain, since we have in every lunar month one full cycle. So this one will not be able to answer it right now until we just do unit 8, because it's really related to unit 8, at least this discussion item. Okay, but if you're reading ahead, you can still answer this one in here. Okay, and it's due September 2nd at 11 p.m. December. It's not December, it's September. Okay. And then we have a quiz that is actually due on August 30th, which is Tuesday of next week. Okay. So those are the assignments. Your reading assignment is again here. Okay. So those are the things that we have them. Units 7, 8, and 9. So those are the ones that we have so far. Obviously, we still have other units. We stop sharing. We share. Before I share that, I really need to switch to student view because there's some stuff in here that's probably share. Well, I'm still working on these things in here. So let me go back. Okay, again. So we have week 1, week 2. So what happened to week 3 and 4? Okay. So I guess I need to make sure I have all of the things lined up correctly. Anyway, so these are some of the stuff you have in here. That at least so far, everything is in great shape, including the discussion that we have in here, which is part of this item. And then I already discussed that. And then you have the quiz, which is actually in here also for you guys. And if I open it as a student, I can look at it right now and start it and do it, okay? And then once I'm done with it, so I can take the quiz. This is actually, let me go back in here. It's very important that you see the difference between the two. So again, this covered chapters 5 and 6. Those are the units 5 and 6 from the previous week. We only have about 12 questions. You have 2.5 minutes roughly per question. You have 3 attempts and the system will register your high score. So here is the trick with quizzes, and it's important that you guys follow this plan. If you score 100% in the first attempt, then you're done. You don't have to worry about it. If you score anything less than that, take advantage of it. Don't leave it that, okay, I have a 98%, so I'm good. No. Since the system takes the highest point in here, why don't I shoot for 100%? Then in this case, go back, review the material again, especially the thing that I was not sure. That's probably the one that messed up the thing, and take it again. Okay, hopefully I can score 100% in it. Obviously, if I didn't score 98, I scored an 81 or even a 73, then in this case, I better retake it again, but take time between your attempts, okay? Take time between your attempts. Do not start it immediately because you're going to do it in a rush and probably you're not going to do as well as you did before. So take advantage of it as much as it's offered to you, and so that you can take full advantage of this thing. Make sense?
Yeah.
Okay, very good. Okay, unless you guys have any question, I'm going to stop the recording and I will see you guys on Thursday. And if there is anything in between, I will share it with you guys. For those in the lab, we have lab on Thursday for section 2. See you guys.